Okay, so this is section C of this paper that we have to do, which is our last section, paper 1, which is physics 2021 GCE science. Someone was saying that you should show your face a little bit more, talk to the people, and so I'm like, no, I'm like an electron. Okay, no one has ever really seen an electron, but hey, the electron has really transformed the world. Electricity, electric circuits, so I think maybe for now, let's go physics. Let's solve as much stuff as possible because COVID has really done us bad. So let's first of all revise, then we'll have a cup of tea right here in time. So section C, question 1, shows a conveyor belt driven by an electric motor carrying suitcases into a trailer of a truck. This truck looks weird. It looks like this is a window from a house. Anyway, I'll not really, but it's supposed to have this and this. Yeah, I know door. The truck has no door. Yeah, something like that. Okay, we move on. Give two differences between mass and weight. Mass and weight. Mass and weight. Hopefully you're able to see properly here. That's my writing there. C1, mass is constant anywhere in the universe, while weight depends on the value of gravity, the value of G. Mass is a scalar quantity, while weight is a vector. Weight is a force, while mass is a scalar quantity. Okay. Next question right there. A suitcase of 20 kilograms is lifted from the ground to the truck. Taking G to be 10, calculate the weight of the suitcase. Just multiply this by 10 to give you 200 newtons. 2, gravitational potential energy of the suitcase. At the top of the conveyor, okay, this is gravity is equals to potential energy is equals to mgh. Mg is weight. Okay, let me just do the calculation. But that was really nice. It's really simple. Our first question, the weight of the suitcase is 200 newtons. Then the gravitational potential energy, GPE, is mgh. Remember, this is mg. This is the same mg up there. So this is wh, weight times height. So 200 times 6 gives you 1200 joules. Okay, 1200 joules. That's your gravitational potential energy. Number C, the suitcase takes 12 seconds to travel 9 meters along the conveyor belt. Calculate the power of the motor. Okay, power of the motor. My approach to this one was that power is equals to work over time. Work is equals to force times distance. Okay, the force 200 newtons times 9, which is the distance, over 12, which is the 12 seconds, gives me 150 watts. 150 watts. That's the power of the motor. Okay. Apparently here, nothing much has been talked about when it comes to the motor, because sometimes this force may differ to this force. Yeah, but the thing is, nothing much has been told, but we've been told we're supposed to calculate the power of the motor if the suitcase covers this much here. Okay, and the only thing we have is the weight of the suitcase. So we'll take that weight as the minimum force that would be needed to lift the suitcase up to the truck. Suitcases. Why not trunks or bags of cement? Where are they going with all these suitcases, like traveling? There's COVID. The electric motor is powered by an input voltage of 230 volts and current of 1.5 amps. Calculate the electric energy input to the motor in 12 seconds. We're looking for energy. Okay. We're remaining. We've scored 8 marks already. I think I'm pretty sure on that one. 8 is ours. 10. We make it. So 10, we make it. The formula for energy or work. This is work is equals to QV. This is charge, that's voltage. Electric energy can also be viewed as electric work. So charge is equals to IT, as I always say. Charge is equals to Q is equals to current times time. So I replace the Q by current times time, because Q is equals to current times time. Q is equals to IT. So current is this, time is that, voltage is that. The energy is 4,140 joules. Okay, that's our energy right there. So in 12 seconds, the electric motor is powered by input voltage of that. Calculate the electric energy input. So the input voltage of this motor in 12 seconds is that much. The output may not be the same, and that's where issues of efficiency may follow. But let's go to the next question. So C2, figure 2.1 shows a square block of glass, JKLM, with a ray of light incident on side JK at an angle of 60. Refractive index of the glass is 1.5. That's our glass right there. Incident ray, this is our normal. The normal is simply a line against the angle of incidence and refraction are measured. Calculate the angle of refraction of the ray. Angle of refraction in the glass. What will be the size, okay, of the angle inside here against this line, which is the normal? My calculation, C2, I use the formula here, which is also known as Snell's rule. Okay, Snell's rule. Therefore, I make R the subject. How do you punch this one on your calculator? Simply say second function sine or shift sine. Check out your calculator. So sine 60 over 1.5 gives me 35. The angle of refraction is going to be 35. When you check out this diagram, it's actually having 60, but the inner angle against the normal is going to be 35 to be smaller, and it's correct because normally the light bends towards the normal as it enters a denser media. Number B, calculate the critical angle for the ray of light in this glass. Okay, the formula here, we go back to this formula which we have come across before. Therefore, refractive index is equal to sine 90. Sine 90 is equal to 1, so just put a 1 there, and then sine C, make C the subject, then you have this critical angle is 42. When the light moving out of this glass is approaching, it's in the glass moving out, if it hammers any of these sides at an angle where it is 42 degrees to the normal, the light will not be directly reflected out of the glass. It will be along the walls of the glass. It will be partially out and partially in. Therefore, that angle will be regarded as our critical angle. D, diamond has a refractive index of 2.42. The speed of light in a vacuum is 300,000 kilometers per second. Okay, 300 kilometers per second. Calculate the speed of light in diamond. Check out this. They are saying kilometers per second. Convert this to meters, SI. Okay, SI unit. So this is, be on the lookout. So speed of light in diamond, they've been given this, meaning there's a relationship between the refractive index and speed of light. So we get to the answer. Did I even answer this? Okay, let's get to the answer. I'll come back to this. D1, speed of light, the relationship between refractive index and speed of light is here. Refractive index is equal to speed of light over speed of light in that given material. Still speed of light in that given material, which is our V. So we make V our subject because that's what you're looking for. Therefore, we will have, this is the speed of light in meters per second. 3 exponential 8 in meters per second. Then our refractive index is 2.4. Then this is what comes 1.42 exponential 8 meters per second will be the speed of light in diamond. Therefore, you should take note to say light is fastest in a vacuum because this is the speed of light in a vacuum. So in any material, it tends to slow down a little bit. And finally, in opaque material, it is blocked. I'll come back to C. Critical angle of diamond, 2 marks, 2 free marks, people. We come back to this usual calculation, which is the same as that one. So we have this formula here written, and then make C the subject. The critical angle is 24 degrees. I look at the other question for C. Explain why the ray of light shown cannot image from KL but will image from LM. Okay, this is K. It won't come out here. It won't go straight like that. Angles on a straight line. It will instead come this way. The reason I think I did mention it, light bends towards the normal when it's moving from a less dense material to a more dense material. So therefore, you find a way of explaining it. English may not be the same, but the meaning should be intact, because when light enters media of higher density, it bends towards the normal. Thus, it will be directed towards side LM. That's my answer there. Let's look at our last question. Our last question, we were told to answer 2, but we can go up to 3. But remember in the exam to follow the instructions, or else you'll be marked in your first 2. And if you get low marks in question 1 and more marks in question 3, they will choose question 1 because it was your first choice. The atomic number of americium is 241. Americium 241 is 95. Americium 241 decays by losing an alpha particle. Explain why smoke detectors contain americium 241 are not harmful to people. Explain why they're not harmful to people. So you should know the nature of these types of decay. My answer is since it decays by alpha emission, alpha particles do not travel far from the source. Thus, less exposure and less harmful. Alpha particles just land a few centimeters from their source. So for you to come into contact with an alpha particle which will penetrate your skin to greater degrees, then you should be very close. The source should be on your skin. Who would be having their source on their skin or in their mouth or swallowing their source? I mean, the source. What would you be trying to achieve? Would you be trying to mutate to become a Superman or what? But the thing is, they drop off just a short distance from the source, so they are less harmful. So don't swallow alpha sources. You won't be Superman. You'll be super dead. Number A2, copy and complete the equation showing this decay by giving values for X and Y. I think you have to understand how alpha decay occurs. I think we already encountered it. One alpha particle, here it has been given helium. Me, I'd given it an alpha symbol. There's no problem. They are called helium nuclei because they are like the helium nucleus without electrons. Okay, so 4, the mass is 4, atomic number 2. Therefore, this mass here will drop by 4, and this atomic number here will drop by 2. So this one will be 41 minus 4. This will be 95 minus 2. Then energy, that's your gamma radiation. So our actual equation is this one here, which gives you 237.93. If you are told to look for this element on the periodic table, go for the atomic number because the elements are arranged by their atomic numbers. The masses, some elements may not be given masses because they are highly radioactive, so go for the atomic numbers. And if you're asked what this energy is, it's gamma rays. Number B shows the activity of a sample of americium-241 changes over a long period of time. Okay, the table is here, number of years, activity or count per second, per minute. I'm used to per second, per minute. So our first question, use these numbers to draw a graph of activity against americium, americano, trapeze americano. Number 2, use your graph to find the half-life of americium-241. I'll answer this just on the graph. My graph is right there. As I said, it's getting late. Let me just, this will be my last question as I subside like a tsunami wave into my, my nest here in the southern part of this world, of this continent. Okay, so graphs, remember, they should always have a title if possible. They should also always have a scale. Okay, a scale, and then their axes should also be labeled. Okay, this is activity per minute. Okay, activity per minute, therefore count per minute. Then my x-axis is time in years. Okay, time in years. I simply do my plotting of the graph. Therefore, my first coordinate, this is activity against time. Okay, so activity is on the y, time is on the x. So this will be 0,64, 500,30, 1000,14, 1500,6, 2000,2. Okay, so you have to come up with a scale on your graph that won't make your graph appear too small. Okay, so this is my y, which is my count, and that's my number of years. Then these are my points of thingy. I've used the pen here, but you can use a pencil. I've used the pen for you to see properly. Yes, so the next question there was saying that we have to find the half-life. Half-life is a period of time that it takes for half a given radioactive sample to decay halfway. Like if you have 10 particles that are undergoing decay, how long will it take for them to decay such that you only remain with 5? And you should remember that half-life is always constant. If the 10 take 2 minutes to decay to 5, then the 5 would take 2 minutes again to decay to 2.5. Then the 2.5 particles will take 2 minutes again to decay to something like 1.7 something. So that's that. So the half-life is simply the total number at the beginning. The total count was 64. You have to look for the half of 64. Half of 64 is 32. So how long will it take for this material to go to half? Your time is here. your count is there. So 64 is your initial, you get to 32 on your graph. Then you project this 32 downwards for you to find the time. So I did this multiply, just in case I didn't plot properly. I did this multiply, that's the half-life. Then remember the half of 32 is what? 16. So I went on 16, I again extended it to the graph, then brought it down here. Half of 16 is what? 8. I went to 8, then extended it and found the time. When I checked the phases of time between these, it was giving me a period of 450 years. Okay, 450 years. So the half-life of this material is 450 years. After every 450 years, whatever remains will decay halfway. After 450 years, whatever remains would undergo decay halfway, until finally, if possible, all of them undergo complete decay and become something else, and we call that transmutation. Okay, transmutation. The last question in this paper, which gives us our last 10 marks, is Californium love. Wow, Californium-241 is also radioactive. Do not be confused by 241, 241. They may have the same masses, but they may differ in composition. That is why I said when you're looking for elements on the periodic table, go for the atomic number. Go for the atomic number. So californium is also radioactive and decays by losing an alpha particle. We already know what happens when a particle decays by alpha. It has a half-life of 4 minutes. Suggests why it would be unsuitable for use in a smoker detector. Look at the half-life. Why would it be unsuitable? It decays at a much rapid rate. So it will undergo transmutation at a fast rate and completely be converted to something else in no time. You need something with a longer half-life for it to live or to last longer. So my explanation, we may differ in English, but let that come out. Its half-life is short, therefore rate of decay is high, which would transmutate the element quicker. This renders californium not suitable for the function or use. Okay, so this marks the end of this paper. I'll see you in another paper, in another video, another time, same place. It's all about pen and paper, not pain, but pen and paper, as long as you're able to see, right? So leave your comments. Remember to subscribe and share this. Remember, for the love of science, we do these things. Bye-bye for now.